In this video, we're going to look at what I like to call the big trig identities. So before you get into proving or verifying trig identities, these are things that you should know. This gives you the best chance of success when tackling a trig identity. So know before you go, the things we are going to look at in this video are the reciprocal identities, the quotient identities, even odd, and Pythagorean identities. So having a great knowledge of these will set the foundation for you to be really successful when verifying. So let's look at these in a little detail. First, the reciprocal identities. So here are the ones you see most often. We know that cosecant is just going to be 1 over sine. Those are reciprocals. Secant of an angle is going to be 1 over cosine. And then cotangent, its reciprocal is tangent, so we know that the cotangent of x is equivalent to 1 over the tangent of x. I think it's also helpful to note that these would work the other way. Sometimes that can be helpful, not always, but it's helpful to know that you could rewrite sine of an angle as 1 over cosecant, and that would work similarly with the other two. So you see it's just a quick rearrangement. We would say the cosine of an angle can be 1 over the secant of that angle, and then you could rewrite tangent as 1 over the cotangent. So you never know when that rewrite will be helpful, but it's just a good thing to note that these would work both ways, even if the first set are a little bit more common. All right, so those are the reciprocal identities. Next, let's look at the quotient identities. So these are functions that can be rewritten as the quotient of two other trig functions. So we have tangent of an angle is sine x over cosine x, and cotangent is its reciprocal. So notice that the quotient just flips. It's cosine over sine. These will be really helpful for rewriting when verifying as well. Okay, now let's look at our even odd identities. So these identities come from the properties of graphs, whether they are even or odd functions. So even meaning y-axis symmetry, odd meaning symmetry about the origin. So here are the properties. And let's first look at even. So to be an even function, for every x, there should be a negative x that also produces the same y value. And so what you can do is replace a cosine of a negative x with a cosine x. So that may be a helpful substitution when verifying a trig identity. Now the odd, so we said that odd functions have symmetry about the origin. So this one, for every x, y on a graph, there should be a negative x that produces a negative y. And so we'll use these as identities. For example, look at sine. If we have sine of a negative input, a negative angle, we could replace that term with negative sine x, and that may be helpful when verifying. All right, so those are even odd. And finally, we have our Pythagorean identities. You'll see these a lot when proving trig identities or verifying. So let's take a look at these. Before I post them on the screen, remember, of course, the Pythagorean theorem is a squared plus b squared equals c squared. So let's think back to a right triangle. Let's do it in the first quadrant of our unit circle. So we can sketch that here. And let's label. So of course we know the hypotenuse is 1 since it's the unit circle. And for this point, we could label the horizontal side x and the vertical side y. But we also know when considering this angle, the central angle, we've found with our basic trigonometry that the x coordinate for a unit circle angle is also going to be the cosine of that angle. So we can label that here cosine of theta. And that's simply because when you take the cosine of the angle, you're really looking at the ratio of the adjacent side over the hypotenuse. So that's x over 1. So that, again, x coordinate is the same thing as the cosine of the angle. And similarly, the sine of the angle is the same thing as the y coordinate because you have the opposite over the hypotenuse for the sine of the angle ratio. So just y over 1. So I make that point so that you can see, sure, x squared plus y squared equals 1 squared, according to the Pythagorean theorem, but we also have a really important identity called the Pythagorean identity that comes forward if we use those trig functions. We have cosine squared, that was the horizontal leg, plus sine squared, that's the vertical leg, equal 1 squared, so 1. And this is our first and arguably the most common one, or at least as you begin to prove trig identities. This one seems to come up a lot. So you want to know it, feel confident with how to use it. I'm going to go ahead and post these identities. I'll at least post the first one. So here it is. And of course, know that because this identity has been proven, we didn't show a specific proof here, not at least a formal proof, but know that you can rearrange it since it has been proven. So you could say, for example, that the cosine squared of an angle equals, subtract sine squared from both sides, so that would be equal to 1 minus sine squared. And of course, you could do all the rearrangements possible if you needed to make a replacement. Say this one would replace 1 minus sine squared with cosine squared, or vice versa. So that can be helpful sometimes when proving. Now, there are many proofs to find the other two Pythagorean identities, but there is a nice shortcut that can help you remember the other two. So those will be ones including tangent squared and secant squared, and cosecant squared and cotangent squared. So to find those, I'm going to show you a nice little trick. First, let's start with cosine squared plus sine squared equals 1 and divide each term by cosine squared. So this is just a little trick to produce another one of the Pythagorean identities. So simplifying that, we would see we get 1 plus, we know sine squared over cosine squared must be tangent squared. And that's going to be equal to, well, we know using a reciprocal identity, 1 over cosine squared must be secant squared. So you can use this next Pythagorean identity similarly to the first. So rearrange it, make any replacements you need as you're proving trig identities. So a quick little cleanup here. As a reminder, here is the second Pythagorean identity that we found. And you can do a similar manipulation going back to that first Pythagorean identity to get the third one. So this time, instead of dividing all the terms by cosine squared, divide by sine squared. So this is just a real nice trick to easily remember your 3 trig identities. So I'll move this down here just to show you how we work through it. We have cosine squared over sine squared. So that uses a quotient identity. That must be cotangent squared. Of course, sine squared divided by itself is 1. And then we have a reciprocal identity. 1 over sine squared is cosecant squared. So this will be your third Pythagorean identity. So now that we've shown that, let's clean this up. And here it is cleanly. Of course, this one can be rearranged and used for substitutions just like the previous two. One more helpful tip that I've heard helps when remembering these if you're looking for an even quicker way. For the second one, I hear a phrase, I tan by the sea, helps you remember that it's 1 plus tangent squared equals secant squared. And then I've heard a slight variation of that, I cotan by the cosea. For whatever reason, that seems to work for some people. So if it works for you, that's a great way to quickly remember these. And in no time, you'll just know these. It'll be second nature. And using them will be the fun part. So hopefully this helped you create the start of a toolbox, know these big trig identities, and you'll be well on your way to verifying trig identities like a pro. I'll definitely be posting videos with some examples of verifying trig identities soon, so check those out. Link will be in the video description. Thanks for watching.